it's actually three of us doing the presentation today, so we'll do a quick roundtable to introduce ourselves. And our apologies for the very large meeting room in which we are sitting, and we appear very small on your screen. But I'm Maximilian talking here, and I'm the Business Development Manager for Africa for our business unit, Integrated Renewable Solutions. And next to me is Denis and Jean-Philippe. Denis?
Yes, I am a research and innovation engineer working for the H2 Mobility. So we are designing refueling stations or technologies to deploy hydrogen for the mobility, for example.
And I'm Jean-Philippe Mauricio, and a technical expert for the batteries and PV solutions inside our LCOS team.
So just to give you a brief overview in a nutshell of what who John Cockrell is.
You're on you're the other way around, I think. We're seeing your side of the presentation. If you can just swap it around. Your slides are small on our side.
Yeah.
Thank you. Perfect. Thank you.
So John Cockrell in a nutshell. So we're a Belgian-based company. We've been around for quite some time, for plus 200 years. We've always been involved in the energy sector, steam engines in the 19th century during the Industrial Revolution, and very heavily involved in the renewables sector and the energy transition for the past 20 years, with a focus on hydrogen, with the manufacturing of electrolyzers and green hydrogen projects, as well as concentrated solar plants. And Jean-Philippe and myself are within the IRS business unit, which stands for Integrated Renewable Solutions. So we work on multi-tech solutions, integrating various sources of renewable energy for industries. And in Africa, we focus mainly on off-grid industries or heavy industries working on weak grids. Few figures, roughly 6,000 employees, over €1 million turnover. We're active. We have subsidiary companies in 19 countries, roughly 80 companies worldwide, and a very diversified engineering and industrial company. So today, as stated by Robert, we'll be talking about battery storage and give you a brief overview of the various technologies around and doing some comparisons. So here's today's agenda, and we'll go through this rapidly so that we can also get your questions and give you the appropriate answers, or write down your questions and get back to you later on. I'll start by mentioning a typical project incorporating multi-technologies that we are currently working on. It's a pilot project, so I'll rapidly run through this, and then Jean-Philippe will carry on with a presentation with the battery storage technologies comparison, and also talking about LCOS calculations between lithium-ion batteries and sodium-sulfur batteries. And then to end the presentation, Denis will talk about green hydrogen and its application in long-duration storage and mobility. So to kick off the presentation, so this is a very interesting project that we are currently working on. As mentioned, it's a pilot project, and it's for a multimodal and multi-technology logistical hub, which will be located alongside a river and connecting a deep water port. I won't disclose the location, as the project is covered by a few NDAs, but it's a good example of what we do and different technologies and solutions that we propose. So basically, we integrate renewables. It's mostly solar. And the objective is to self-consume the energy produced on site and obviously to globally reduce the emissions of CO2. So as mentioned, it's multimodal because there's barges, hydrogen and electrical barges. There are trucks, electric trucks, hydrogen buses, forklifts. There are self-driving vehicles. I'll run through this. And it's also the opportunity for us to highlight some technological innovation linked to green mobility, energy storage, and the digitalization of the site, which will be monitored to, at the end of the day, achieve a very competitive cost in terms of kilowatt hour. And globally optimize the operations of the logistics center. This project is being developed with two other partners. One is involved in the logistics and the other one in construction. And our scope is obviously related to the renewables and the energy production and the whole integration together with the energy management system. I wanted to also highlight our value chain for this project and globally for the other projects that we work on. So we are involved in the whole value chain. We analyze our customers' requests in terms of either cost reduction, CO2 reductions, technical constraints with, for example, availability of steam, etc. And we carry out an audit and technical feasibility study. We use very powerful tools and software to design based on economical constraints, design the optimal plant for our customers. And provide a full technical offer, including the scope of works, the single line diagrams, full quote. We carry out the project in terms of EPC with subcontractors and in terms of O&M, thanks to our EMS, energy management system. We provide the dashboarding of the plant, the monitoring, and anything relating to the optimization of the maintenance and the effectiveness of the site. As mentioned earlier, it's a multi-tech project. So we have fast chargers scheduled on the site. The most powerful fast chargers will be 350 kilowatt fast chargers for trucks. So we have electrical trucks, but also hydrogen-powered buses that will be working on the site. We have vehicle-to-grid operations. We have battery storage, lithium-ion batteries. It's a multimodal hub, so we'll have barges transferring containers from the riverside port to a deep water port. We'll have a hydrogen refueling station for hydrogen buses and hydrogen barges. The whole EMS and digitalization of the site with the monitoring and the forecasting based on the weather forecasts and the grid services, and also self-driving shuttles on site. The focus is obviously on the renewables. It's a large site, so there's space available. We'll have 15 megawatt peak of rooftop solar. We'll have 14 megawatt hour of battery storage. A John Cockerell manufactured electrolyzer of 5 megawatt with storage facilities and refueling stations for the hydrogen buses and barges, and then a whole station of fast chargers and regular chargers for trucks, forklifts, electrical vehicles, buses, train that will be operating on the logistical site, and also for the few electrical barges which will be operating. That's it for the brief overview of a typical multi-tech and multi-model project. I leave it to Jean-Philippe to cover the battery storage technology and comparison that we have carried out based on the various technologies.
So Maximilian, just a quick question before you go, if you couldn't mind, just on the previous slide. Apologies, I was just waiting for you to finish. If you can go back to your last slide. So the last slide of your presentation. Okay, yeah. So conscious that this is quite a small facility relative to a lot of the clients on this call. Some have smaller facilities, some don't. The average mining load is in excess of 50 megawatts all the way up to 1,000 in this client base. Do you see that a similar split of different types of technologies will be utilized when you start getting to other types of applications? So I know it might be different technologies, but are you also seeing 8 or 9 technologies being, so it's incremental gains across technologies as opposed to one silver bullet, so to speak? Thank you.
Yes, and that's typically our focus when we work on projects, and we aim at projects that integrate multi technologies. And definitely the load on mine sites is above 50 megawatts. Obviously, those mine sites have space available, so limitations in terms of solar is not really a constraint. But we definitely wish to integrate electrolyzers when there's excess of solar, fast chargers for electrical vehicles that are starting to appear on mine sites. I know that there are a few pilot projects for heavy dump trucks, but there's also all the ancillary vehicles that could be integrated and incorporated on mine sites to reduce the carbon footprint of these mining operators. So yes, definitely a multi-tech integration, which could also concern the battery technology. I mean, you could have, and that's, we've already worked on such projects. You could have alongside a battery storage system, lithium-ion batteries working together with sodium sulfur batteries. This is a combination that could be considered definitely.
Well, thank you. I mean, one last question, and I know we said we'd waited to the end, but just like the energy space, what we say today is different to tomorrow. But I know it's a general question from Mark, is technology integration issues. I don't know if you can just touch on any experiences, obvious things to concern. And I know it's project specific, but a generic comment would be helpful. Thank you.
One concern is, and this is typically a topic that we work on in Europe, is the grid services part of our projects. I mean, some mines are grid connected, others are off grid. But the grid services is something that may be an issue in a few countries where the regulation is not always in place. But could be definitely pushed by mining operators, which represent a large scope of the GDP of some countries. But that may be a constraint, is the regulation around the grid services, which in some cases helps us to optimize the global kilowatt hour cost of the projects that we implement.
Cool. Thank you very much. Apologies to interrupting, Jean-Philippe.
Okay, on this side, we have a small overview of different parameters and characteristics that each battery technology has. And okay, the first one is vanadium redox flow batteries, which is a challenging technology for the battery, not exactly very spread around, but okay, it does exist. The main issue with this technology is that the cost is quite high. But on the other hand, it has the advantages of totally decoupling the power and the energy capacity, allowing you to size the battery exactly how you want for your own application. Second column is lead acid. It's just here for historical reason, but we do not use them in our project. Lithium ion is the main technology we can find everywhere. We mention here two different chemistry, NMC, which is mainly driven by electrical vehicles, and not so far used for stationary application. LFP is also used by Chinese mainly for electrical vehicle, but is the main solution we used for stationary application. And the last one is sodium sulfur, mainly produced by NGK, Japanese company. And these are the two last, the main technologies that we consider in our different projects.
So a question
Yes.
for you, Jean-Philippe, perhaps.
Yes.
The two lithium options in our world at the moment, we tend to see that if you go out on an EPC contractor quote, you only get lithium firm bids. I know not valid for long periods. The other sort of technologies are still marketing documents, but where would you use the two lithium, and you can use them together, but can you just give examples of where you'd use these two technologies using the same commodity but different applications, just for the benefit of the team? Thank you.
Yes. Here at John Cockrell, we do not consider to use an MC chemistry, mainly for safety reasons, because the thermal stability of this technology is less. And okay, everybody knows, I have seen some car burnings and runaway burning thanks to, because of the battery. The main advantage of the NMC and the reason why it is used in electrical vehicle is the density, which is much higher, is the best of all those technologies. The energy density is higher, so you need less space, and it's easier to fill a car with this technology. LFP is much more stable, and okay, for stationary application, we're not reaching or not searching generally to have the maximum density. It's not a big issue if you have let's say 1.5 the volume, if you have 2 times or 1.5 times the number of containers. So it's much safer, and we really do prefer to work with LFP for our stationary application. So
Thank you very much. Perfect.
Yeah.
Thank you.
Yes, one can say also that okay, NAS technology is quite interesting. We will see that it's quite cheap, but on the other hand, it's a 6-hour, more 6-hour application, and you do not have the same ability to size your project with NAS than you have with lithium. With lithium, you can have different C rate, 0.5, 1 or so, and it's easier to find the solution for your specific application with lithium ion LFP. NAS is more constrained in this point of view, but we will see that it has very interesting financial
economical advantage.
Maybe you can go to this next slide.
So this is a third point, which is a LCOS price comparison between the lithium ion and sodium sulfur batteries based on a specific project that we are implementing in Africa.
Yes, this is the tentative to compare the cost of the two technologies. Lithium ion is LFP, of course, and okay, the exercise of the LCOS is depending of the hypothesis you take, and so it's important to know in which context you make your calculation. It's not a perfect way to compare two technologies, but in the same frame, you can identify the advantage of one against the other. In this calculation, we made the assumption, those assumptions that, okay, the capex is related to the price of the batteries in an engineering, procurement, and supervision project for Africa, meaning that the construction on site, the erection is not included in the capex, mainly because it really depends of the size of the country, and usually we used a local company to make this part. So we didn't want to introduce this parameters inside the calculation because it's not in our hand. Also, the battery is supposed to be used for one cycle a day, every day in the year, and during 20 years. And the energy, which is the electricity price, which is an important factor in this calculation, is supposed here to come from a PV plant. And with the amounts of energy you can produce with PV in Africa, we arrived after calculation to a price of 50 euro per megawatt hour of energy. And finally, the auxiliary load are not considered because if you increase the OPEX by integrating the price of the auxiliary, you may find at the end different figures. And on this point of view, lithium is not always the best one because in hot countries, lithium needs HVAC, and HVAC may be a high load at the end. NAS technology is high temperature technology, meaning the battery is working between 300 and 340 degrees Celsius. And so it doesn't need to be cooled down with an HVAC. It's only cooled when needed with a simple fan. So the load of the auxiliaries are much lower, maybe much lower, depending on the context, with the NAS than it is with the lithium ion. But okay, it's not included in this calculation. And by comparing different discount rate and different price of energy, you can see that actually the price of the NAS technology is much more interesting than the lithium ion. This, I have to precise that this is mainly due to the capex because of the huge increase of the lithium, the raw material, these last 2 years, and the actual price of the lithium ion battery is very impacted by this. And 2 years ago, the figure were completely different, but nowadays it is what we reach. Also, another point which has a quite important effect in this calculation is the degradation of the battery over 20 years. NAS battery do not degrade as fast as the lithium. On the other hand, the round-trip efficiency of the lithium is better all along the life of the battery. Also to mention that the lithium-ion manufacturer do not guarantee the battery for in this situation for 20 years. Usually it's less than 20 years. And if you make the calculation on 15 years, for example, the advantage of the NAS is increasing also. So globally, for our consideration nowadays, we are very interested with the NAS battery technology because of this advantage.
So these are not high-level prices because it's an existing project for which we've quoted both lithium-ion and NAS batteries with active prices, and these are figures that we've shared with our customer. So whatever the case, the LCOS definitely goes to the advantage of NAS batteries. which price is very, very stable for obvious reasons, which are also highlighted in the comparison table. So I mean, the final decision will be up to the customer, but based on the LCOS price, it's pretty straightforward.
So perhaps one comment and two questions, if I can, at this, because I think this is a great slide. So the first comment is Cresco also does a lot of mining feasibility studies, and we're currently doing a few in the lithium space. And what we are seeing is that you have the good lithium mines have already been built and operating, or even maybe at the end of their resource life. The new lithium mines that are coming out, unfortunately, are not on the low-cost production curve. But if your price point was $6,000 2 years ago, the mine didn't look very sort of viable. But at $71,000 a ton, you could imagine what the IRR in the mine is. So the question is this a long-term view price, or is this a short point? And that obviously affects the financing of the mining side. So that's just a comment. The question, however, well, there's two questions. One is on the safety comment earlier, but I'll get to that. I think it was mentioned earlier that NAS is only currently produced by one company out of Japan, I think it was. I don't know if you can touch on that, because yes, on the lithium side, price volatility. On the NAS side, is there supplier limitations?
Yes, on the NAS side, for the moment, we know NGK in Japan. Also, German company BASF is also involved in this technology and is working with NGK for this.
Yes, they have a JDA. They have a joint development agreement to further deploy the NAS batteries, both in terms of technology and in terms of production capacity.
And NAS, okay, it's sodium and sulfur. Sodium is okay, you can find it everywhere. Sulfur is a side component of petroleum industry. You can find it. It's cheap and it's a residue, in fact. And the cells are made of metal aluminium, and the container is made of aluminium. It's all okay, easy to find and cheap material. So the price of the NAS is quite stable, as it is not the case for the lithium. The price of the lithium exploded these last 2 years. And okay, this is a figure for today, so we cannot say it will be the same in 10 years. But who can know how the lithium price will evolve? Okay, we all know that the lithium will be used more and more, and at the end it will be a rare, very rare material, because mainly the lithium industry is driven by the electrical vehicle manufacturers. So I don't believe that the price of lithium will slow down in the coming months, no, and coming years too.
And if John Cockrell was asked to provide a fixed price EPC on NAS, do you believe the technology is developed enough for you to take that construction risk?
Well, we're already working on projects which implementing NAS batteries, and we're very confident. We have a lot of projects in the pipeline with NAS batteries, and we'll be implementing the first NAS battery in Africa before the end of the year.
Okay, brilliant. Good answer. That's great to hear. And then there was one other question that's come up. I think it's from the previous slide from Dragon. It says, what does ++ stand for in terms of safety?
Well, okay, as mentioned, okay, lithium is okay. You have some issue with an NMC. It's much safer for LFP. In case of the NAS, the technology is existing for more than 20 years now, and in the world's history, there have been one single fire of a container, and following this event, the manufacturer stopped the production, redesigned completely all the product, and made a battery of tests, deep test, so that nowadays we can be sure that the technology is really safe. Compared to lithium, who everybody knows many cases of fire with lithium application. So yes, we are very confident that this technology is safer than lithium one.
I think that the safety tests that NGK carry out, it also involves some container dropping from a certain height with damages to the container and no single issue in terms of fire. So it's a very stable technology, both in pricing and in safety.
Also to mention, you have many cells in one single module. They also made a test of burning one single cell, and the fire did not spread to the remaining cells in the module. So even if you have a specific, an issue on a single cells, you will not have a complete container burn.
Perfect. Thank you very much.
I think we can carry on to the last part of our presentation, which covers green hydrogen applications.
So here's an example of the application and the activities of John Cockerill with the whole hydrogen activities, from the electricity generation to the delivery of the hydrogen. So once we have the electricity, we provide electrolyzing unit, which makes the hydrogen out of water. We are providing all the stack separation and purification skids. Then we need to store these hydrogen and to deliver the hydrogen to different customers, which can be industry, gas grid, or mobility like cars, bus, trucks, or even boat. Then why choose hydrogen? Because if we face the hydrogen mobility against battery electrical vehicles, you find that the efficiency is not better, it's worse. That's right. But a vehicle working with hydrogen will need more energy at the beginning from electricity to the wheel to run. So you have a global efficiency of 30% for the fuel cell electric vehicle, and globally more or less 50 or 60% for the battery electric vehicle. But you have large difference for the using of these vehicles. For example, hydrogen cars can reach up to 1,000 kilometers with one fill, and the filling duration is 5 minutes. Against the battery electric vehicles, it's more or less 600 for the better, and with a duration of 30 minutes for the
fast charger.
Fast charger, yeah. So this is a different scenario that you can find, and where the hydrogen is more competitive than battery. And I give some examples just here.
And we've ordered a few Toyota Mirais for our site here in Belgium. So we'd be happy to tour you in our new cars anytime. Feel free to call in.
For example, some example that has been installed where each time the hydrogen solution was more competitive than the battery. The boards were studied, and I give here the main reason why they choose the hydrogen against the battery vehicles. Because, for example, for the bus in Pau, you have a better range with the bus than the battery ones, and you need less investments for charging infrastructure. For example, you need less buses because when the bus needs to be recharged, you cannot run. And if we think about using pantograph to charge it, it will cause some issues with the flexibilities of the bus line. When you have some works on the manifestations or some events during all along the line, you cannot change the road of the bus. And that would lead to have an oversizing of the fleet of by up to 75% with the battery vehicles. For another example with boat, if you use batteries instead of hydrogen, you have a much heavier boat, which is causing an excessive spend of energy. And you need also a network to charge the boat, which is up to 2 megawatts, which is really high power. We don't find this kind of connection in harbor or small harbor like for leisure, for example, for this case. But with hydrogen, you can schedule you can store the hydrogen more easily, and you can fill it much faster. And that was also the reason that they choose this solution. So for mobility, hydrogen is really a good solution for heavy mobility, and you have to think about mobility as a service and not only the efficiency. I continue with some example of the two main storage system and transport system of hydrogen now. One is compressed hydrogen in the container or in bundles in tanks, the cylinder tanks that we can find at the left side. You can store hydrogen up to 1,000 bars. This is required to have a good storage density. And this is one of the more economic in the long term, because you don't need much energy to store it, because storing hydrogen costs energy. You have to compress the hydrogen to a very, very high pressure, and this is really spending a lot of energy. The other technology is liquefied hydrogen, and for this technology we need to cool down up to cryogenic temperature, which is really cool, and this is really spending a lot of energy. It's 12 kilowatt by kilo of hydrogen is a third of the energy capacity of the hydrogen. So you lose a third of the energy by storing it with liquefied hydrogen. But you have some density which is really high. This is a better storage density that you can find now, and it is usually used, for example, for aerospace, for rocket space, for example. This is liquid hydrogen that is used. And it will be made probably the way we can transport hydrogen in the future by using a large boat that you can find on the right side.
For example, from Namibia to Europe.
For example, yeah. Another example, if you want to use hydrogen as a electricity sources, you can coupled with a fuel cell stack. And for example, with a container of 40 feet, you can store 33 megawatt hour of energy and use it for 6 hours at nearly 3 megawatt hours. So this is really a high powerful and high density storage system. It can be also used as it is scheduled to be the best way to make seasonal storage also with, for example, storing hydrogen in salt caverns. that can store a really big amount of hydrogen and store it for months and release them as we want.
I think that's it from our side.
I have a few questions, if I can, on the hydrogen, and then I think there are a few that have come in the box. So we can go back to your first slide, please, the one with the typical process. So a lot of our clients have existing infrastructure at the mines or other areas, which also include existing water and storage facilities, pipelines. I mean, obviously, every client is very specific. Do you see the opportunity to reuse any of this infrastructure, and therefore it's not all greenfields capex, or are there limitations perhaps you could touch on?
Yeah, there's clearly some limitation because hydrogen is not gas. This is not the same pressure, and this is not the same chemical properties. Hydrogen will damage steel pipes because of embrittlement, and we cannot use pure hydrogen in common steel pipe that we use for gas, for example. But you can make some retrofits on vehicles, for example, on dumper or trucks, on this kind of, or even forklift. This can be done. I know that it exists, but this is really a complete new infrastructure because of the electrolyzing stack, the storage. This is not the storage with compressed hydrogen, for example, is using carbon fiber tanks. So it's not the same technology.
But in terms of pipeline transport,
yeah,
a blend is possible with gas and hydrogen.
Yes, you can blend up to 15% the gas pipe, the gas network. This is already done in some countries, but this is really the limit. So you cannot have 100% hydrogen. You have to mix it up to 10 or 15%, because also of the final user, which are using some, for example, burners for the cooking or for the boilers. We have a different behavior with hydrogen and full 100% of natural gas.
But we have carried out already here in Belgium tests using the existing pipeline system with a blend of gas and hydrogen.
Okay, if you can go to thank you. If you go, so there's 3 slides on 3 questions on the chat. I'll just have one more from my side, and please bring them in. So if you go to your last slide, please, Tini. We've spoken about large mines with significant loads. We also have certain clients on the call who have less than 1 megawatt loads, generally, unfortunately, in built-up areas and that. So the 40-foot container, 33 megawatt hours, is actually of interest. So this is obviously the storage component. How much area would you need to have that convert to an energy equivalent so that you can sort of support the hospital or the telecoms? So roughly, you have a 40-foot container, and that there's generally car parks or small areas around these sites. But how much more space or infrastructure would you need to be able to take that storage into real energy? Is it another 40-foot container or 3 or 4 of those, just roughly?
For the conversion, it's more or less the same, I would say. It's not the conversion unit is it's quite a high power density. Let's say that is a fuel cell stack. I don't have in mind the size of 1 megawatt fuel cell, but I would say the size of a container.
Okay.
So to be honest, I'm not sure about that. I've seen some installation with picture with this kind of power, but don't want to give fake data.
So I mean, we've seen some of the sort of the diesel engine players where they have the diesel energizer in one 40-foot container, the water in one, and the fuel in the other, I imagine that sort of configuration might work if you have space limitations.
Yeah.
Great, thank you. We have 3 questions on the chat. So first one from Mark again, thank you. What about storing H2 as ammonia? And I know that is quite a broad question and different people are doing different things, but you mentioned Namibia as an example. I know they have lots of ambitious plans. I don't know if you can touch on that quickly, please.
I don't know a lot about this storing of ammonia, but I know that ammonia is a kind of dangerous material also. Can be dangerous for humans. And you have also the conversion from hydrogen to ammonia, and use the ammonia as a power source, because ammonia, when you burn it, you make nitrous oxides, which is a high
polluting.
High polluting material, which is high
CO2 emissions.
Emission of greenhouse. It has a really high greenhouse gas effect. So probably it will come up, but for instance, I don't know any project that use ammonia as a media for the transport of hydrogen, for green hydrogen.
Next question from Lo is the acronym LOHC. If you can just unpack that. I think we all know LCOE and LCOS, but just unpack that acronym for us, please.
Yes, LOHC is quite a new technology, quite promising. It's not really used, for instance, because it has some limitation, also because of the conversion from hydrogen to the material, and you have to think about all the product lifetime and product life cycle, because once you have removed the hydrogen from the LOHC, so for the people who don't know what is LOHC, it's a liquid organic hydrogen carrier. So you can transport hydrogen within this carrier as a liquid or solid. It can have a interesting density, but it has also lower cinetic, for example, or purity of the hydrogen which coming from this LOHC is also an issue when you want to use it with a fuel cell, for example.
Thank you. Then I guess the next 2 questions are linked in a way. So for large yellow equipment, dozers, excavator graders, or even all the way to 40-ton dump trucks, do we see conversions from diesel to BESS or H2? If this happens, do we need to replace the equipment, or can you just replace the engine or components? And then the next question, which is linked to that, is do we see for those sort of applications, do you believe it's going to favor BEV or FCEV, using the acronym? And Andrew, you can jump in here if there's no clarity on what that question is. Thank you.
Yeah. I would say that for these kind of dumpers, if you would replace the diesel engine by the either thermal hydrogen motor or electric motor, it can work. I know that it has been done already. And the other question was.
So do you need to, you just replace the motor? And the second one is
the conversion.
What do you believe is the favored technology choice for conversion for large equipment?
Fuel cell or a battery?
Fuel cell or battery. That depends clearly with the use of the truck or because if you need really to use it every time a day, you don't have to. You can't wait for the charging to be done with battery electric vehicles. because it can spend hours to charge. And you maybe want to charge it when there is sun, because you don't have enough storage to store the electricity. So for this kind of use, I would say that hydrogen is better because you can store hydrogen more easily than electricity in batteries, and you can fill the truck really quickly in a few minutes, and so you don't have dead time by fueling the vehicle.
Great, thank you very much. We have 5 minutes left, so if there's any last questions, I'm happy to take some hands at this stage. Thank you for everyone who's put the questions on things there. If there's nothing from the audience, I have one last question, which is the big blue sky gazing question is hydrogen.
Robert, you ran out of questions. Sorry.
Yeah, we're done. That's why I've got one more. I'm trying to fill the space. I don't want to give anyone 4 minutes, but to put the John Cockrell team on sort of on the podium a little bit is how long before we see hydrogen at scale offsetting large demand? So I'm conscious you showed a nice project, but it's actually quite small demand there and that. But when do we see mining fleets being replaced, or large bus fleets, or even applications in the energy sector? Is it 5, 10, or even longer away if we had to guess? Because as part of our energy strategy work, we're guessing, and it'd be great if you had you can make it a range, so we're not putting it on the spot. Thank you.
We don't have any crystal ball in terms of consumption, but we do have a crystal ball and a strategy when it comes to production, because we have the ambition to have a production capacity of 8 gigawatt for the manufacturing of electrolyzers by 2025, with the various plants that are actually running that will be increasing the production capacity, and the new plants that are currently being built around the globe. So that doesn't answer your question, but at least in terms of production capacity, we'll be ready to serve the market and implement green hydrogen projects with our electrolyzers. So that's for the promotion of our activity. I had to put this in. Emphasize this. In terms of consumption, I think that depends on the market, the price of the commodities, the price of the minerals as well. Any investment that yellow machine manufacturers would want to make, R&D. I mean, some of them have already done this and have dumpers running in South Africa, at least one. But there are also other tests being implemented right now. So I think it's a global dynamic that needs to be carried by both the users, the manufacturers, and with the uncertainty of the commodity market that we're seeing globally right now. So it's a tough question to answer, but it does require some dynamics from all the stakeholders.
I think that was a good answer. At least you didn't disclaim for 10 minutes and then give one answer. So thank you, excellent, and thank you to the rest of the John Cockrell team. We really appreciate it. As mentioned to everyone, the recording will be available along with the presentation and along with the contact details for the team here. We hope to further engage. We believe these technologies are coming and definitely part of our energy strategy planning. Might not be procuring today, but in our view, not too far in the distant future, it'll be there. Thank you very much, everyone.
Thank you, everyone. Have a good day.
Thank you. Bye.
Thank you.
Bye.
Thank you.
Bye-bye.
Thank you.
Bye.
Bye-bye.
Thank you.
Thanks, bye.